Hello everyone, my name is Fian Yang. I'm the Technical Marketing Engineer for the Cisco CSR 1000V. Today I'm going to introduce a new solution called Secure DMZ by extending your Transit VPC with Cisco CSR 1000V. So we are going to talk a little bit about the Secure DMZ overview, and then we're talking about how we automate this solution, also about the solution details and the automation details, as well as the source code if you are interested to try off the template. Okay, so this is the Transient VPC design we have with Amazon on the internet. So if you want to have a multiple spoke VPC in your network, you can connect your spoke VPC in this topology ABC into the Transient VPC, as well as your on-premise network, for example, your private DC. In the Transit VPC, we'll have two CSR that's standing in two different AZ, providing high availability for your application. And the CSR will establish the BGP and GRE tunnel to the spoke VPC and establish an IPsec VPN connection. And based on the IPsec VPN, the CSR can exchange the routes with the virtual private gateway in your spoke VPC. So the spoke VPC can learn routes from the other spoke as well as your private data center. And this whole solution is a baked solution, so you can launch this solution through a CloudFormation template, and it will have kind of the Lambda function running as a script in the background. So whenever you have a spoke VPC want to connect, you give the VGW a specific tag, and the whole solution will help you to connect the connection and send the configuration to the CSR, and tunnels will be up. And we have seen a lot of customers have deployed this type of topology in many scenarios. And the other question after building the hybrid cloud connection is, how do you secure my internet access, and how can you turn this Transit VPC into a secure DMZ? So today we are going to talk how we transform this solution into another secure DMZ. Okay, so this secure DMZ, if you're looking at the topology, you will see we adding mostly two elements. So one is called the FTDv. That's the Cisco Firepower Threat Defense Virtual Appliance. And we also have another FMCV, so that's the Firepower Management Center Virtual Appliance. So they are all supported on the Amazon Marketplace, and the FTDv will be acting as a sensor. The FMCV will be acting as a controller to control the provisioning configuration of the FTD. And in this case, the routing will be changed, that the internet traffic from the spoke will hit the CSR, and then the CSR will redirect the internet traffic to the FTDv. So the FTDv will acting as a egress IPS. It will inspect the internet traffic, and then it will send out the traffic to the internet. Also, the other way will work the same way. When the internet traffic hit the FTD, it will be inspected again and then sent to the CSR, and CSR will send traffic to your spoke VPC or to your on-premise as well. And in this case, since the spoke resource need to access the internet resources, so there will be a NAT happening. So we will also use the FTDv as a netting device on the edge to net the source IP into a public IP. And let's talk a little bit more about the automation. Since you have already known the Transit VPC, the whole solution will be launched through a CloudFormation template, and we will try to reuse the CloudFormation we have and make this secure DMZ another automated solution. So this solution can also be launched through one click in your CloudFormation console. It will create all the Amazon components, including your subnet, route table, FTDv, FMCV, and also the instance, EC2 instance used by the CloudFormation template. the CSR is already created by the previous Transient VPC template. So this template will use to provision the CSR, and we will also use the Amazon Lambda function to provision the CSR. Manual provisioning are also needed because the Cisco FTDv, FMCV doesn't have the correct API we need today, so you have to configure this part manually, and I will show you two different ways to configure these solutions in the next few demos. Okay, so before we start, let's assume you already have a Transient VPC that's running, so you should have this Transient VPC created. It's using the 10.0.0/16 subnets or setter block, and by launching this Transient VPC, it will automatically create two subnets. So subnet 1 is 10.0.0.0/24 that will be used by the CSR1. The second subnet is 10.0.1.0/24 that will be used by the CSR2. And the Transient VPC template, it will also create a management route table that will pointing the default route to the HW, so the CSR can talk to your spoke through a default route and point to the HW in this case. Those two CSR are in different AZ, so CSR1 is in AZ1 and CSR2 is in AZ2. And to better demonstrate this demo, I also created a spoke VPC already, and the spoke setter block will be 20.0.0.0/16. I also created a Linux virtual machine that will sit in the subnet of 20.0.1.4. So the IP address is 1.4 for the Linux virtual machine. And I already tagged the VGW in the spoke, so the connection, the tunnel is already built up. Okay, so let's take a look what we need to add into this type of solution to make it work. So the gray area, as I mentioned, is the one that will be created by the Transient VPC already. And let's take a look at what more should be created in this solution. So we will launch FTD virtual appliance in this solution, and we will put in one of the AZ. Since the subnet cannot be across different AZ for single subnet, so in this case, I will create a CSR1 FTDv subnet. That's the 5.0 will be attached to the CSR1. It will be used to connect to the FTD. And also on the CSR2, since it's in another AZ, so I will create a 6.0 subnet that will be used by the CSR2 to connect to the FTD virtual. And on FTDv side, I will create a FTDv inside subnet. That's the 4.0. will be used to connect to the CSR1 and CSR2. Since those three interfaces are in different subnet, so I give them a kind of pattern. Is on the FTD virtual, it's gonna be 4.4, and on the CSR1, it's gonna be 5.5 IP address, and on the CSR2, it's gonna be 6.6. Since they are all in different subnets, so they will be connected by Amazon internal gateway, or we can call that route table. So I will create another FTD virtual route table to connect those three interfaces. The reason it will be connected is after the connection has been made, FTDv will establish the BGP connection to the CSR so they can exchange routes with each other. Also, since the FTD or the Transient VPC solution it will use a different wharf for different spoke. So in order to make this solution to work, I will create a separate VRF on the CSR as well. We call it FTDv wharf. So in order for CSR 5.5 IP address to reach out to the 4.4, I have to add a static route on the CSR to let it know if you want to talk to 4.0, you should talk to your route table first. So I will add a static route on the CSR1. It's listed here. Also, the route has to be added on the CSR2 as well when it has to talk to the FTD inside interface, the 4.4 with the CSR 6.6 IP address. So as reversely on the FTDv, the static route has to be added as well. We want to talk to the 4.subnet, 5.subnet, and 6.subnet. It will use it internal gateway, the 4.1 as the next hop. The reason we want to add the default route to using another subnet that will be introduced later is that's the outside interface. It will be the default route pointing to the internet. Okay, here comes the FTDv outside subnet. So that's the 7.0 subnet. On the FTDv, we will have a 7.224 IP addresses. The other part is the FTDv virtual will be acting as a sensor, so you have to have a controller or central management tools to manage all the configuration or the provisioning or the IPS policies. So that's FMC virtual. And this FMC virtual will be using the same subnet 1. So that's a 0.0 subnet. I just make it another here. It's better for understanding, but that's the same subnet as the CSR1 it has. And it will talk to the FTDv virtual through that channel for management. Since that's the management route table, so that's the same route table with the route table here on the upper management route table. So those two route tables are actually the same. So it has all the same default gateway pointing to the HW as well. So that's how it connects to the internet. And the HW, the two HW in these slides, they are the same HW as well. Just for better understanding, I just separate them, but they are the same HW. Okay, so let's recap what we have in the existing resource and what we have to create in the new resources. So in the existing resource, we have a Transient VPC, we have two CSR, we have two subnet, and we also have a route table that will be used to point to the management route table. And we have HW as well. We also have a spoke VPC, that's the 20 subnet, and it has a Linux virtual machine, and it has the related subnet route table HW as well. For the new resource we need to create, it will include two instances, that's the FTD virtual, FMC virtual. They will be connected through a subnet 1 through the management subnet, and we will create 4 subnet in total. So we have CSR, we have a CSR1 FTDv, that's the 5.0. We have CSR2 FTDv subnet, that's the 6.0. And we have the FTDv inside subnet, that's the 4.0. And we also have FTDv outside subnet, that's the 7.0 subnet. And please remember, each subnet are in different AZ because they have to title to different virtual machine in different AZ. And we will create a route table called management route table. It will associate with the subnet 1, subnet 2, and FTDv out. For the FTDv route table, it will associate with the subnet with CSR1 FTD virtual, CSR2 FTD virtual, FTDv inside subnet. So those are the resources we need to create. Okay, before we go into the demo how we create the resource, let's talk a little bit more about the detailed design. So since the Transient VPC will use different VRF for different spoke, which means on the CSR1 here, if we have two spoke A and B, you will see on the CSR you will have spoke A VRF and spoke B VRF. On the CSR2 you will have the same as well. And in this case, to make it work, we will create another FTD virtual VRF, and we will put another interface, that's the gigabit 2 interface. When I'm talking about the CSR1, it's going to be in the 5.0. So this IP address will be the 5.5, and this IP address will be the 6.0, and it's going to be 6.6. And FTDv will build the BGP connection. It's going to be a multi-hop BGP. Why it is a multi-hop? Because they are in different subnet, if you remember. So the FTDv inside interface actually is in the 4.0, and the other two interface in the CSR is 5.0 and 6.0. After the eBGP configuration, has been established between the FTDv. The FTD virtual will send the eBGP default route by default information originates to the CSR, and the CSR will include the same route target as those VRF. So the VRF A will learn the default route through the FTDv WRF. And also, the default route will be sent to the spoke VGW, and spoke VGW will install this default route in the spokes route table. So when the virtual machine sends a packet, the packet will hit the VGW, the VGW will forward the traffic all the way from VRF A, FTDv VRF, FTDv inside, FTDv outside to IGW. So that's the way how the internet traffic will be redirected all the way from the spoke to the CSR, to the FTD, and to the IGW. So that's how the internet traffic works. And in order for you to better troubleshooting, sometimes you need to reach out to the VGW through the FTDv WRF. So in that case, you have to do a redistribute connected on your FTDv VRF. So the subnet direct connected will be redistributed into the other VRF, so they can learn from that VRF to better troubleshooting. Okay, so here is the FTDv design. On the FTD, actually, I will also enable the NAT because as I mentioned in the beginning, the spoke virtual machine need to talk to the internet resources. So when the traffic hit the FTD, the source IP address will be the virtual machine's IP address. That's gonna be a private IP, and that IP will be NAT into a public IP, or that's not a public IP specifically. It's gonna be the FTDv outside interface IP, and that IP will be netted again on the IGW by Amazon. So this is a two-step NAT. So on the FTD, I will turn on the NAT inside on the inside interface and turn on the NAT outside on the outside interface. And inside of the FTD, I will enable the access control IPS and URL filtering, mobile and file inspection. And on the FTD, I will use AS number for the BGP 65002, and the AS number on the CSR will be 64512. Okay, so before we have talked about the control plan, that how it built, but since we add another hop, that's the FTDv route table or Amazon internal gateway, we have to fix the data plan as well. So what we will add is we'll add the multiple routes here on the FTDv route table. The first two routes is the spoke setter block. In order for this route table to reach out to the spoke, it will use one of the CSR as the next hop. So that's why we will add a static route here. Because whenever the FTDv have the packet from the internet, and that packet will be sent to the spoke virtual machine. If you remember in the beginning, the FTDv will use the Amazon internal gateway as the next hop, so that when the packet hit the internal gateway has to know how to forward the spoke traffic. So that's why we have to add the spoke subnet on the route table to let it know how to forward the traffic. It will use CSR1 as active, the 5.5, and CSR1 and CSR2, they were working as a HA pair. So when the CSR1 reboot, it will fade over to the CSR2. The second or the last route table is default route. That's used by the route table to forward the internet traffic to the FTD. Because when the CSR1 have the internet traffic from the spoke, it will forward the traffic to the FTDv route table as the next hop. And the FTDv route table will know exactly what the default route should be forwarded to. So that's why we add another default route on the FTDv route table to let it know if you receive the internet traffic, just forward to the FTD virtual appliance. That's why those routes are needed for the data plane to work. So let's give you an example how the traffic flow will looks like. So assume we have the traffic from the internet and it will need to talk to the spoke. It will comes all the way from the internet, HW, management route table, FTDv, and it will send to the FTDv route table. On FTDv route table, it will do a lookup and it will match, okay, this is the packet that will be sent to my spoke A with subnet 20 subnet. And then it will use the next hop as active CSR1 to forward the traffic. And the CSR1 receives the traffic in the FTDv VRF, and it will do a lookup. It will know, okay, this route should be sent to the spoke through a different wharf, so it will send to the VHW, and VHW will receive the traffic. It will forward to the virtual machine. Let's look in the other way. So this is the spoke to internet traffic. The spoke will send the traffic through the HW, through the VPN gateway, all the way to the CSR1. And CSR1 do the route lookup. It will see, okay, this is a default. It should match my default route and send to the FTDv route table. On FTDv route table, it will do a lookup. This is internet traffic. It will be redirected to the FTDv virtual appliance inside the interface. So it will send to the FTDv. FTDv will forward the traffic to the outside, and it will do the NAT. It will send to the HW. So that's how it gets to the internet. That's how it works from the routing and netting perspective. And we will verify this type of connection in my second video of the hands-on demo. How do you allow SSH HTTP traffic from the Google, so you can access this type of resource from your virtual machine inside of the spoke. This is SSH. I will use it as a laptop, SSH public IP, and it will be netted into a private IP, so I can log into the virtual machine in the spoke A. And in the spoke A, I will try to access Google. Since I have enabled the HTTP, HTTPS, or the type of connection, so I will be able to access Google. The second one is I will block the HTTP, so I will also SSH into the virtual machine in the spoke A, and I want to do a HTTP access. Now, since HTTP connection has been removed or the policy has been removed, so I cannot access it from the Linux virtual machine. As you can see, there is a whole lot of things need to be created in this solution to make it a secure DMZ. So I will demonstrate the demo in two ways. The first one probably is the most easiest one. Is I will create all those stuff manually and in the Amazon console, so you will know exactly how it works and which type of configurations need to be done manually. And the second way or alternative way is I create the CloudFormation template as well as the Lambda function to push the configurations. So in that case, it's an automatic way to provisioning all the resources and the configurations. And I will show you the link of the GitHub, which has all my source code, and you can take a look and have a try. So let's go to the demo.